We're going to be using the methodology from Chapter 11 to predict Lewis dot structures for some simple molecules. These are ones that meet the octet and the duet rules. So we'll start off with the most basic and the most simple, and it's the kind of thing that you need to practice. You just need to be able to get the hang of it. It's not something that you can memorize. Anyway, let's just get started. Hydrochloric acid or hydrogen chloride. So, to do this Lewis dot structure, I see there is no central atom. So, I just line them up and notice that they're going to be covalently bonded because they're both nonmetals. And I count up the number of valence electrons. So for hydrogen, there's 1 in group 1. For chlorine, there's 1 in group 7, so a total of 8. So I have 8 valence electrons to try to make every atom happy. So how do I distribute them? First into the bonds, and then to the outer atoms. So 1, 2, 3, 4, 5, 6, 7, 8. And then that's it. So hydrogen has 2 dots around it, emulating 1s2, or is similar to electronic configuration of helium. And chlorine has 7 of its own, but is claiming to have 8, like S2P6, which is the octet rule. So hydrogen is happy because of the duet rule, and chlorine is happy because of the octet rule. So there is no central atom, so there are no regions of electron density. The shape is that it's diatomic, and there are no bond angles. So the next one is oxygen. So again, 2 atoms, covalently bonded. There is no central atom. So I add up all the valence electrons, and I have 12 valence electrons. So first into the bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's my valence electrons. I don't have any more. So now I look for the octet rule. So 2, 4, 6, 8. This one is happy. 2, 4, 6. That one is not happy. So what do you do if this is you? You have enough valence electrons and your very close friend doesn't. Well, maybe you'll end up sharing. So I can take any of these electron pairs and turn them from non-binding electron pairs into bonding electron pairs. So now I have 2, 4, 6, 8, 2, 4, 6, 8. So both atoms are happy because of the octet rule. So again, there's no central atom, so there's no region of electron density, and the molecule is diatomic, and there's no bond angles. Next is nitrogen. So again, 2 nitrogens, they're both nonmetals, so they're going to be covalently bonded. So I count up all my valence electrons. This time I have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all I got. So 2, 4, 6, 8, that one's happy. 2, 4, that one's not happy. So again, we'll have to share. So I'm going to take non-binding electron pairs, turn them into bonding electron pairs. So let's check again. 2, 4, 6, not quite happy. So I'm going to do it again. So now this nitrogen has 2, 4, 6, 8. This one has 2, 4, 6, 8. And both are happy because they're meeting the octet rule. Again, there's no regions of electron density because there is no central atom. It's diatomic and there's no bond angles. Carbon dioxide. So I'm looking at carbon dioxide, and I'm thinking that carbon will be the central atom. For one, there's only one of it, it's the least abundant, and carbon likes to form 4 bonds, whereas oxygen likes to form only 2. So I would predict that carbon would be the central atom. Now I have 2 oxygen atoms, and I will put around it in a symmetrical way. Symmetrical because electron pairs repel one another. And then I'm going to put covalent bonds because they're all nonmetals. Now I want to check to see if this is valid. So I count up all the valence electrons. I have 4 from carbon, 12 from oxygen, so a total of 16. So first, into the bonds, 2, 4, 6, 8, then to the outer atoms, 10, 12, 14, 16. Is that right? 2, 4, 6, 8, 10, 12. Wait, 2, 4, 6, 8, 10, 12. Oh, 14 and 16. You got to count your electrons correctly or you will get the wrong answer or won't be able to get a good Val-Lewis dot structure. So now I have the 2 outer atoms are happy, but carbon is not happy. Carbon has only 4 valence electrons around it. So from either one of these, doesn't matter which one, I'm going to take some non-binding electron pairs, turn them into bonding electron pairs. Now, carbon has 2, 4, 6, so it's a little bit happier, but it's not quite happy. So I'll go to the other side and take 2 non-binding electron pairs, turn them into bonding electron pairs. So now, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, everybody's happy. So this is a Val-Lewis dot structure. So now I count the regions of electron density. I have 1, 2. Don't be confused and say there's 4. A region of electron density could be a double bond, a triple bond, or a single bond. So I got 2 regions of electron density. The way to get them as far apart as possible is to have a linear relationship, and the bond angles would be 180 degrees. So let's go back a little bit and look at the models. So with hydrogen chloride, here's a model for that. So hydrogen has the 2 electrons here, and the chlorine has 2, 4, 6, 8 over here. Okay, so it's simply diatomic. If I look at oxygen, now my models don't let me show you the non-binding electron pairs on each of the oxygens, but there's the double bond. If I look at nitrogen, here is our triple bond, and you can see that there's only 2 atoms, so there is no regions of electron density. So on this one, I'm able to show you the non-binding electron pairs, which will again be as far apart from one another as possible. And when we get to the carbon dioxide, here's the carbon, here's the double bonds, here's my outer oxygens. Again, I don't have the atoms that would be able to show you the non-binding electron pairs. However, they don't affect the shape of the molecule. So next, we have formaldehyde. So notice that we go from the periodic table from the left side to the right, just like how we read. And so that's why hydrogen is on this side, and then carbon, and then oxygen. But what I have to do is figure out which one is the central atom. So it's not going to be hydrogen. Hydrogen can never be a central atom because it only forms 1 bond. It's either going to be carbon or oxygen. So carbon forms 4 bonds, oxygen likes to form only 2, so I would predict carbon would be the central atom. Now I have 3 other atoms to put around it in some sort of a symmetrical way. Something like this might work. So now they're all nonmetals, so I'm going to put covalent bonds between them, and this is what I would predict. What I have to do now is prove that that is true by showing that all of the atoms can meet the octet rule or the duet rule. So I have to count up all my valence electrons. So I have 2 hydrogens, that gives me 2 electrons, 1 carbon, which gives me 4, 1 oxygen that gives me 6 more, so a total of 12. So first into the bonds. 1, 2, 3, 4, 5, 6. Then to the outer atoms. The hydrogens already have enough. 6, 7, 8, 9, 10, 11, 12. So there's all my valence electrons. So now I have to see if all the atoms are happy. So each hydrogen has 2 electrons, so that's the duet rule. This has 8 electrons, so that's the octet rule. But carbon has only 6 electrons around it. So I have to find an atom that can share. The hydrogens cannot share. They don't have any extra electrons. But I can take from the oxygen those non-bonding electrons, turn them into bonding electrons, and now I have a double bond. So I have 3 regions of electron density, so the shape is planar trigonal and the bond angles are 120 degrees. So here's a model for this. So here I'm letting carbon be the silvery one. These are the hydrogens. Here's the oxygen, and I have the 2 non-bonding electron pairs as far apart from one another as possible. Now looking at this structure, there's only one central atom, and that's the carbon. And the carbon has 1, 2, 3 regions of electron density. Again, it doesn't matter whether that's a single bond or a double bond. So next, we have carbon tetrachloride. So I'm seeing that chlorine likes to form only 1 bond, whereas carbon likes to form 4 bonds, and there's only 1 of it. So I would predict carbon would be the central atom. Then I have 4 chlorine atoms to put around it in some kind of a symmetrical way. Then they're all nonmetals, so I'm going to covalently bond them. So that's what I would predict. Now I have to prove that by using the valence electrons. So I count up all the valence electrons. I have 1 carbon, gives me 4, 3 chlorines gives me 21, 1 hydrogen that gives me, I'm sorry, the wrong one, 4 chlorines that have group 7, so 28, so a total of 32. So first into the bonds. 1, 2, 3, 4, 5, 6, 7, 8. Then to the outer atoms. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. That's all of them? Yes. So did I meet the octet rule for every atom? There's 8 here, 8 here, 8 here, 8 here, and 8 here. So the answer is yes. So it's about a Lewis dot structure. So I have 4 regions of electron density around the central atom, making it tetrahedral, and the bond angles are 109.5 degrees. So here would be a model for that. Again, the chlorines, I don't have room for the non-bonding electron pairs, but the shape is determined by how many reds are bonded to the central atom. That's the only thing that matters. So you can see it's tetrahedral, it's got 4 sides. So here's 1 side, 2 sides, 3 sides, 4 sides. And each angle is greater than 90 degrees. It's 109.5 degrees. Anyway, moving to the next one. So what we've done here is we've taken off one of the chlorines here and replaced it with a hydrogen. But we'll go through the same process. So which one is going to be the central atom? It would have to be the carbon. It's the least abundant and the one that has the most number of bonds it can form. So I would predict the carbon would be the central atom, and I got a hydrogen and 3 chlorines to go around it. So maybe some kind of a symmetrical way like this. Now they're all nonmetals, so be covalently bonded. That's what I would predict. Now I have to prove it by adding up all the valence electrons. So 4 from carbon, 21 from chlorine, 1 from hydrogen gives me 26. So first into the bonds. 1, 2, 3, 4, 5, 6, 7, 8. Then to the outer atoms, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Is that what I have? 26, that's all I have. So I see that the duet rule is satisfied here, the octet rule for the central atom, octet rule, octet rule, octet rule, every atom in there is happy. So, just like the previous example, we have 4 regions of electron density, so it should be tetrahedral with 109.5 degrees bond angles. So here would be an example of this molecule. Okay. So again, each angle 109.5 degrees. Now the 109.5 degrees is in a perfect world where all 4 of these have equal repulsion value. It's not going to be exactly 109.5 degrees because the hydrogen is going to have a different repulsive value than the 3 chlorines. But we only need to know the basic angles. So the next one is nitrogen trichloride. So I'm looking at this, I would predict the center atom to be nitrogen. Then I have 3 chlorines around it in some kind of a symmetrical way. And they're all nonmetal, so they're going to be covalently bonded. So then I need to count up all my valence electrons. So I got 5 from nitrogen, 21 from chlorine, give me a total of 26. So first into the bonds. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I got 2 more left to go. Where do I put them? All the other atoms are happy, so they go on the central atom. So I check for octet and duet rules. So 8, 8, 8, 8. Every atom in there is satisfying the octet rule. So this is about Lewis dot structure. Now, I have 1, 2, 3, 4 regions of electron density, making this a pyramidal molecule, bond angles 109.5 degrees. So here would be a model of that. This would be showing you the non-binding electron pair. The reason why this is not flat or planar is because these electron pairs repel the other electron pairs, giving it depth. So we just call it pyramidal. There's other ways to describe it, but pyramidal is good enough. Okay? Again, 109.5 degrees. The next one is oxygen dichloride. So I would predict that the central atom would be oxygen. So there's the central atom, 2 chlorines around it. They're all non-metal, so covalently bonded. So I count up all my valence electrons. So I get 6 from oxygen, 14 from chlorine, giving me a total of 20. So first into the bonds, 1, 2, 3, 4, then to the outer atoms, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So how many more do I have? 20. So 17, 18, 19, 20. So now I look for the octet rule. So 8, 8, 8. Every atom in here is satisfying the octet rule, is happy. So that's about Lewis dot structure. So what about the number of regions of electron density? I have 1, 2, 3, 4 regions of electron density here. So that means that it's bent, it's 109.5 degrees. So I guess I'll just make it from here. So here would be a model representing oxygen dichloride. So this is oxygen, here's the 2 non-binding electron pairs on oxygen, and here's the outer chlorine atoms. And again, I don't have the atoms that will show you all the non-binding electron pairs on the chlorine atoms, but it doesn't matter. The only thing that matters is the reds that are on the central atom. So this is a bent shape. Okay, it's bent because of these non-binding electron pairs on the oxygen, pushing these other ones down. Now a variation on that would be hydrogen-oxygen chloride. So there are other names for this. Let's just name it as an acid, but we won't bother with that now. So I got to figure out which one is the central atom. It's not going to be hydrogen, it forms 1 bond. It's not going to be chlorine, it forms 1 bond. Oxygen forms 2. So I would predict it would be oxygen. So oxygen would be the central atom, and I have a chlorine over here and a hydrogen over here, and they're all nonmetals. And now we have to prove that that's possible. So I count up all the valence electrons. 1 from hydrogen, 6 from oxygen, 7 from chlorine, give me a total of 14. So then, first into the bonds. So 1, 2, 3, 4. Then to the outer atoms. Well, hydrogen is already happy, so that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So yes, I have 14 valence electrons. So now I check for the duet and the octet rules. So hydrogen has 2, so that's satisfying the duet rule, like 1s2, like helium. Oxygen is S2p6, in other words, the octet rule. So is chlorine. So every atom in there is happy. So I have about the center atom 1, 2, 3, 4 regions of electron density. So 4 regions of electron density, so the molecule is bent with bond angles 109.5 degrees. So here's a model that could represent this. So here's oxygen, the only central atom. It's bonded to a hydrogen and to a chlorine. And the oxygen has 2 non-binding electron pairs that push these other ones away and make this bent shape. So here on this atom, I have ways to show you the non-binding electron pairs on the chlorine, even though they don't affect the shape of the molecule, which is simply bent. So now we're going to look at nitrite ion. So I'm looking at this, and we use the same methodology, even though it's a polyatomic ion. The center atom would be nitrogen. So nitrogen surrounded by 3 oxygens. They're all going to be covalently bonded because they're all nonmetals. And then, to keep track of all the charges and all the electrons, I'm going to put this in brackets so I can make sure I don't lose track of that -1 charge. So this is what I would predict. Now I count up all the valence electrons. I got 5 from nitrogen, 18 from oxygen, and that -1 means that 1 more came from somewhere. If it was sodium nitrate, it would have come from the sodium. Anyway, to show that ionic bond, you could just put the sodium out here like this. So this represents the ionic bond, but these are the covalent bonds within the polyatomic ion. So anyway, I count up all my valence electrons. I got 24. So first into the bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's all I got. So I check for the octet rule. Happy, happy, happy. Nitrogen has only 6 electrons. So what we need to do is a double bond. So this double bond could be formed from either one of these 3 oxygens. It doesn't matter which one. So if I do it from here, now, this has 2, 4, 6, 8 electrons around it. So we meet the octet rule. So this is a valid Lewis dot structure. So I have 1 central atom and 3 regions of electron density around it. The double doesn't matter whether it's a double or a single bond. So that means that the shape should be planar trigonal and the bond angles are 120 degrees. So here's a model. So here we have the central nitrogen. Here's your double bond right here. So 1, 2, 3 regions of electron density. And here's the non-binding electron pairs that do not count towards forming the shape. So you can see that there's 360 degrees in a circle. You divide it into 1, 2, 3 equal parts. So each angle here is 120 degrees. So the next one is nitrite. So similarly, I look at nitrogen as the central atom. I have 2 oxygens to go around it in a symmetrical way. They're all nonmetals, so I'll covalently bond them. And I have to put that -1 charge here so I don't forget about it. So that's what I would predict. So I count up all the valence electrons, 5 from nitrogen, 12 from oxygen. That -1 means that there's 1 more, so a total of 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I put in all my valence electrons. So now I look for octet and duet rules. So here's 8 over here, here's 8 over here. Nitrogen has only 2, 4, 6. But it's bonded to 2 oxygens that are both capable of forming double bonds. So we're going to share, we'll just use this one. So now nitrogen has 2, 4, 6, 8 valence electrons around it. It's happy. So that's about Lewis dot structure. I have 1, 2, 3 regions of electron density that all are going to repel one another. So the shape is bent. So here I'm taking the one I made for the nitrate, and all I have to do is take off one of those oxygens, and now I have the nitrite. So you can see that the shape is bent. It's not linear because this non-binding electron pair on the nitrogen is pushing the other ones down. So the bond angle here, approximately 120 degrees. So next, we'll look at sulfite. So sulfur can form 2 bonds, so can oxygen, but sulfur is the least abundant. So I would predict it would be the central atom. So the central atom, and I have 3 oxygens to go around it, some kind of a symmetrical way. And they're all nonmetals, so I'll put a covalent bond between them. That's what I would predict. And again, make sure you don't forget about that -2 charge. So I count up all my valence electrons. 6 from sulfur, 18 from oxygen. That -2 means 2 more. That's a total of 26 valence electrons. Again, first into the bonds and then to the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, I got 2 more to go. 5, 26. So did I meet the octet rule for all the atoms? Yes, 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 yes. So I would say this is a valid Lewis dot structure. So I have 4 regions of electron density. 1, 2, 3 that are bonding and 1 that is non-bonding. So the shape should be pyramidal. So here's a model of this. So the blue is the sulfur. You can see the 1 non-binding electron pair right there. And I got 3 that are bonding to oxygens. And in this model, I can show you the non-binding electron pairs on each of the outer atoms. So it's pyramidal, okay? And so the bond angles are 109.5 degrees. See, greater than 90, greater than 90, okay? Then we have sulfate. So the center atom would be sulfur. And I have 4 oxygens to go around it in a symmetrical way. They're all covalently bonded because they're all nonmetals. And then I put the brackets because I don't want to forget about that -2 charge. So that's what I would predict. So I count up all my valence electrons. 6 from sulfur, 24 from oxygen. That -2 means 2 more, so a total of 32. So first into the bonds, then to the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Did I do that right? Yep, 32. So then I check for the octet rule. So 8, 8, 8, 8, 8. Every atom in there is happy. So I have 4 regions of electron density, all far apart as possible. That gives me a tetrahedral shape. So here was sulfite. So the difference between sulfite and sulfate is simply 1 oxygen. So here comes an oxygen, looking for 2 more electrons to call its own. And here is the molecular shape for the sulfate ion. So this is a polyatomic ion. There's 2 electrons more than protons in this entire entity right here. So this would be attracted ionically to a sodium or a magnesium or something like that. So then we move into the situation where we have more than 1 central atom. So the key to understanding this right here is that you have 2 central atoms. They're both carbon. So this is key to understanding it. Now, around that pair right there, I have 4 chlorines to put around it in some kind of a symmetrical way. And they're all nonmetal, so they're going to be covalently bonded. So that's what I would predict. So I add up all my valence electrons. 8 from carbon, 28 from chlorine, give me a total of 36. So first into the bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 3, 4, 5, 6, and 7, 28, 29, 30, 31, 32, 33, 34. Did I get them all in there? No, I got 2 more to go. So I'll put them on one of the central atoms. I don't know where else to put them. So, did I meet the octet rule? 8, 8, 8, 8, 8, only 6. Okay, so this carbon right here is not happy yet. So I need to make a double bond. Do I take from the chlorines? The answer is no, because chlorine on the periodic table, you can see it wants to form only 1 more bond to become like a noble gas. So carbon can share. So I take these non-binding electron pairs and I put them over here. So now I have 8 and 8. Everything is satisfying the octet rule now. So the 2 central atoms both have 1, 2, 3 regions of electron density around them, making this planar trigonal, and the bond angle is 120 degrees. So in this model, I show you the double bond in the middle, and here's my 4 outer atoms over here, my 2 central atoms, and each one of the central atoms has 1, 2, 3 regions of electron density, making it planar trigonal, and bond angles 120 degrees. So 360 degrees in a circle divided by 1, 2, 3 pieces. Each piece would be 120 degrees. So next one is another polyatomic ion, the oxalate ion. So again, you have to recognize that there's 2 central atoms. So you start off like this. Now we have 4 oxygens to put around this in a symmetrical way, and they're all nonmetals, so they're covalently bonded. But this is polyatomic ion, so I have to make sure I have a way to keep track of that -2 charge. So when I count up my valence electrons, okay, I got 8 from carbon, 24 from oxygen, and that -2 means that there's 2 more, so a total of 34 valence electrons. So first into the bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the outer atoms, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, to 334. Did I do that right? Yes, I got 34 in there, okay? So now we check for the octet rule. 8, 8, 8, 8, only 6. This one has also only 6. So this carbon cannot share with the other carbon because it's already deficient. So this carbon can share with either this oxygen or that one. It doesn't matter which one. If I take these non-bonding electron pairs, turn them into bonding electron pairs, now this has 8, this has 8, this has 8. Now I look at this carbon, has only 6. So it doesn't matter which oxygen I take it from. Okay. Now every atom in there is happy. So each central atom has 1, 2, 3 regions of electron density. That makes it planar trigonal, and the bond angles 120 degrees. So here's a model of this. So here's the 2 central carbons with 1, 2, 3 regions of electron density. Here's one double bond, here's the other double bond, and this one's able to show you the non-bonding electron pairs on the outer atoms, which really don't affect the shape. Okay. Then, nitrogen tetroxide. Again, I have to recognize that there's 2 central atoms. So I got 4 oxygens around it, some kind of a symmetrical way. Then they're all covalently bonded. And then that's what I would predict. So I count up all my valence electrons. I got 10 from nitrogen, 24 from oxygen, so a total of 34. So first into the bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Is that all? Yes, 34 valence electrons. So now I check for octet and duet rules. So 8, 8, 8, 8, 2, 4, 6, 2, 4, 6. Again, those nitrogens don't have enough valence electrons. So they're inadequate each one, so they can't borrow from each other, similar to what happened up here. So I need to make double bonds with one of the oxygens. So if I do it from here, now that nitrogen has 2, 4, 6, 8 electrons. If I do it from here, 2, 4, 6, 8 valence electrons. Every atom is happy. And again, we could use this same model, okay? So you can see that it doesn't really matter with the models. You can move them around. You have free rotation about single bonds, okay? So now the last one that we'll do in this video is rather complicated, and I wouldn't expect you to go from here to a complete Lewis dot structure, but I'm going to show you how it's done. So this is giving you some information. So it means that the nitrogen is bonded to the carbon. This carbon is bonded to the other carbon. These hydrogens are up on that other carbon. And now that carbon is bonded to the other carbon. And these 2 oxygens are bonded to that same carbon. So something like this. Now that hydrogen is bonded to that other oxygen. So yes, going from here to here takes a little bit of practice and more things to learn. And again, I wouldn't really expect you to know how to do this. This is more of an organic chemistry molecule. But I just want to show you that it works for all molecules. So I added up all the valence electrons. So 5 from nitrogen, 12 from carbon, 12 from oxygen, 3 from hydrogen, so a total of 32. Again, burst into the bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then to the outer atoms. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. How many do I have? 32. 31, 32. Okay, So I put in all my valence electrons. Now I'm going to check for the duet and octet rules. So this hydrogen is happy. This oxygen, 2468, is happy. This one, 2468, is happy. That carbon, 246, not happy yet. So we need to share 2 electrons with it. So now, do I take it from this oxygen or from this oxygen? If I were to take it from this oxygen, that would mean that oxygen would have 3 bonds. Oxygen doesn't form 3 bonds, it forms at the most 2. So therefore, I'm going to take it from here. So now, 2468, that carbon is happy. 2468, that's happy. 2 and 2, that's the duet rule. 2468, that carbon is happy. What about the nitrogen? 2, 4. That nitrogen is not happy. So we're going to have to share, and the only atom in the vicinity is the carbon. So I'm going to take these non-bonding electron pairs, turn them into bonding electron pairs. 2, 4, 6, not quite happy. So I have to do it again, make a rare triple bond. 2, 4, 6, 8, 2, 4, 6, 8. Now every atom is happy. So this organic molecule is both a nitrile and a carboxylic acid. So here is a Lewis structure for this. Okay. So here, if this nitrogen is the yellow, here's the non-bonding electron pair. Here's the nitrogen and the triple bond right here to the carbon, a single bond, and then those 2 hydrogens bond to that carbon, and then here's my carbon to oxygen double bond with the non-bonding electron pairs. Here's the carbon to oxygen with its non-bonding electron pairs, and here's the hydrogen. So if I look at this molecule, look at the central atoms. This central atom has 1, 2 regions of electron density, so therefore it's linear. This central atom has 1, 2, 3, 4 regions of electron density, all have atoms on it, so it's tetrahedral. Bond angles, 109.5. This central atom has 1, 2, 3 regions of electron density, all atoms on it, so it's planar and trigonal. Bond angles, 1, 2, 3, is 120 degrees. Then we have one more central atom, which is this oxygen right here. 1, 2, 3, 4 regions of electron density. 2 have atoms, 2 do not, so the shape is bent, 109.5 degrees. So anyway, we'll have some more videos when I get a chance. This is going to give you a good start.